Okay, welcome back. We are still reviewing momentum and impulse. Uh, Let me remind you what we discussed in our part A or part 1 of this momentum. We went through the definition. Now we know when we are talking about momentum, we are discussing the product of mass and velocity of an object. And then we looked at the nature side of a momentum as a vector. We said momentum is a vector because it has both magnitude and direction. We went on discussing also what could cause a change in momentum. We've all agreed that the change in momentum is due to the fact that there will be a change in velocity of the object, but the mass of that object remains or stays the same or constant throughout the entire process of changes. And then also we landed by discussing Newton's second law of motion in terms of momentum. We've said second law of Newton in terms of momentum states that the net force acting on an object is equal to the rate of change of momentum. That's where we stopped on. So now moving from there, part 2, under momentum still, we are going to look at the law. So in your test or during exams, they will tell you, take note of this, they will tell you to state or define the law or principle of conservations of momentum. So it doesn't matter which word is being used, define, state the law or principle of conservation of momentum. So that law, so as we can already from the get-go, law, it's something you cannot just alter. It's guided by principles. So that law states that the total linear momentum of an isolated system remains the same. Let me put it up for you. The total linear momentum of an isolated system. An isolated system stays constant. Now, I would like us to scrutinize what has been put up there. Total linear momentum of an isolated system. Let us deal with that word there. Isolated system. A system. More. We start with isolated. When we're discussing isolated, this isolation is referred to as a closed system. So this one here is a closed system. That system means what? Is sealed. Meaning what? There is no external force that is able to act on that system. It's well isolated. So no external force is acting on there. No external force acts on that system. So it separated from the rest. Whatever is going on around the system happens within. So it is isolated from the external things that are taking place there. It is sealed. For instance, if you have a sealed water bottle, there is no other properties that will be able to do what? To penetrate. Why? Because it's sealed. So such system is isolated because it gives room to no any other external factors to come and interfere with the properties of the substance inside the bottle. So when we are talking about that, we are referring to this exactly. It is an isolated system. So you'll find out that in your examination guideline, they will say that stays constant. That stays constant can also be referred to as remains the same, okay, remains the same, remains the same, or is conserved. So these are the words that comes there. So the total linear momentum of an isolated system stays constant, remains the same, or is conserved. What does that mean? By the way, there's always a question this part of the work here. What that means is this: it is isolated. The total linear momentum before is going to be equal to the total linear momentum after. So there is the relationship of that statement. By the way, take note of this. In physics, most of the time, this is how the construction of the question comes. They give you a scenario. First question, they tell you to define. You give your definition. Afterward, they will tell you calculate. Calculation has to do with the application of what you discussed in your definition. So we've just said now that the total linear momentum of your isolated system stays the same. The application of that, or the implication of it, means what? Total linear momentum before is going to be equal to the total linear momentum after. That's the relationship. The total linear momentum before equals to the total linear momentum after. Meaning you will have M1 V1 plus M2 V2. Some textbook, they use A or B to denote the same thing, 1 or 2. So initial in bracket equals to M1 V1 plus M2 V2 and everything there final. So from here, you pay attention now. They will tell you an object A approaches object B coming with this velocity, carries this mass, and then they make contact, and then afterward, this one goes this way, that one goes that way. Calculate the velocity or the mass. You have those kind of scenario there. So this quickly takes us to one thing that I would like us to clarify quickly here: collision theory. Okay, so that takes us to a principle under what? Collision theory. A collision theory. So you will have now, the idea behind it is objects or bodies are going to be making contact. They will be colliding one against another. Collision theory. You have two different types of collisions under this part of the work. The first one is when your collision is elastic. So when you are talking about elastic collision or inelastic collision. So we have two types of collision. Objects are making contact, elastic or inelastic. Now, let us try to analyze them. A collision is known to be called elastic when the total kinetic energy before is going to be equal to the total kinetic energy after. So meaning EK total before equals to EK total after. What causes in physics, I would like to remind you, any object that is moving, what causes the movement is kinetic energy. Kinetic energy is responsible of all movements in physics. So, because these objects are going to be colliding under the influence of kinetic energy. And by the way, just a quick reminder there, kinetic energy, the formula is mass, velocity of this object, all squared, divided by 2. So it's half mv squared. We will deal with that in details when we work out work energy and power. So what's going on? A collision is known to be called kinetic elastic when the total kinetic energy before collision equals to the total kinetic energy after collision. Meaning what? There is no loss in momentum. Meaning your momentum there was what? Conserved. Give you an example. Normally, this part of the work, they will give you a scenario whereby they say two cars are coming, one from the right, another one your left-hand side, boom, head-on collision. After collision, they immediately come to a stop or to rest. So after collision, none of them move. They come and stop. They collide, they stop. Such collision there is elastic because after collision, there was no movement that took place. Momentum was what? Conserved. So it is elastic. And part B of it is inelastic. When you're discussing inelastic, it means there was kinetic energy that was transferred to the system even though they collided. Afterwards, they transferred energy upon them. So this object moved for a bit of time before they came to rest. So such collision is inelastic. Under elastic, momentum is conserved. Total kinetic energy before will exactly be equal to the total kinetic energy after. Under inelastic, the total kinetic energy before will be different. That value will be exactly different from the total kinetic energy when after their collision. So that's the major difference there. Question can come to you and say, investigate or establish through calculation if this collision was elastic or inelastic. In order for you to prove that, you must work out what? The kinetic energy of the entire system before they collided. You compare it against to the total kinetic energy of the same system after collision. If they are of the same value, that collision was elastic. If the values are different, the collision is inelastic, to tell you that momentum was not what? Conserved. So we've come to an end this part of the work. You stay connected. Part 3, we discuss impulse and then the rest follows through. Thank you.